Hello everyone, welcome to today's calculus notes for section 4.2. Today we're going to be talking about area, and we're really going to start laying the groundwork for our definite integrals and kind of understanding what exactly an integral is and what we're finding when we find an integral. So in order to do that, we'll start talking about sigma notation. So let's talk about our definition. The sum as k goes from a to n of a function f of k is listed out here. And so we see this symbol right here is a capital Greek letter sigma standing for sum. K is your index of summation. So k starts at A, which is your starting index, and goes to n, which is your ending index. And then f of k right here is an expression that describes each term in the sum. And so here's how it works. It's the sum of all f of k's, starting where k is a, and going all the way up to where k is n. And it goes up sequentially by 1. So it's going to be f of a, our starting index, and then a plus 1, a plus 2, so on and so forth, to n minus 1, all the way up till we get to our ending index of n. And if we add all these values up, that would give us the sum as k goes from a to n of f of k. So let's go ahead and try this in an example. So here we want the sum as I goes from 1 to 6 of the function I. So all we need to do is start with our index and substitute 1 in for I, and then we're going to substitute 2 in for I, and then 3 in for I. And this is just going to keep going up by 1 until we get up to I equals 6, which would be right here. And so to find our sum, we want to add all these together. Well, it's 3, 6, 10, 15, and 21. Now for letter B, now our function is I plus 1, and we want to find the sum as I goes from 0 to 5 of I plus 1. So we're going to substitute 0 in for I, and then we're going to keep increasing I by 1 all the way up till we get to 5. So if we increase that by 1, then we go up to 1. Okay, so follow the I there. And then I is going to go up 1 more, and it's going to be 2. So following the I. And then it's going to be 3. There's your I. Then we go up to 4. All the way up until I reaches 5. Okay, so these were your I's all along from 0, 1, 2, 3, 4, up to 5 of our function I plus 1. And so we could add these together. This is going to be 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15, plus 6, and that gives us 21. Alright, I want you to try letter C on your own now. Alright, welcome back. You should have gotten this for your work and 135 for your answer. Next we want to talk about expanding each sum. Now we want to go, as k goes from 1 to n, find the sum of 1 over n times k squared plus 1. So notice in this case we have two variables. We have an n variable and we have a k variable. And you can see that those two variables are right here as well. So again, we do the same thing where we substitute our starting index in for k. So we get 1 over n times, well, 1 squared plus 1. And then we would increase that k by 1. So it's still 1 over n times 2 squared plus 1. And this is going to continue until we reach n. But because we don't know what n is, we're going to just go ahead and put an ellipsis here, saying that this continues in the same manner. So then we do 1 over n. And just like this part has f of n minus 1, we're going to include that here as well. So we're going to go all the way till we get to n minus 1 for our k value. And then we're actually going to finish with f of n. So we get plus 1 over n times n squared plus 1. All right, so this is how we would expand this sum that looks just like this. All right, I want you to try letter B now on your own. All right, welcome back. Here is the expanded sum for you. Notice we just start with 1, go to 2, continue the pattern all the way up to n minus 1, and then ending here with n. So let's talk about limits of summations. So here are some summation formulas and their properties. Notice each of these is the sum as I equals 1 to n. So we've got to start from 1 and go to n. And this first one here is the sum as I goes from 1 to n of c, where c is a constant. And that sum is going to equal c times n. If we have the sum as I goes from 1 to n of I, it equals this formula, n times n plus 1 over 2. And I've also written it in standard rational form, n squared plus n over 2, because it's a little bit easier to find our limits then. Moving forward here, this is the sum as I equals 1 to n of I squared. And we have n times n plus 1 times 2n plus 1 over 6. Or in standard rational form, 2n cubed plus 3n squared plus n over 6. For number 4, now we have the sum as I goes from 1 to n of I cubed. This is n squared times n plus 1 squared over 4. And in standard rational form, we get n to the 4th plus 2n cubed plus n squared over 4. So those are the 4 main ones that you're going to be using to find the limits of the sums. Now, we also have a couple properties here, and this is the sum as I equals 1 to n of a sub I plus or minus b sub I. So if we have two functions added or subtracted here, we can really split them at the addition and subtraction and find each sum separately. In number 6, the sum as I goes from 1 to n of k times a sub I, where k is a constant, well, what you can really just do is factor out that constant and then just find the sum of your function a sub I. So number 1, it says evaluate the summation. So here we have the sum from I equals 1 to 200 of I. Now if we were to just find the summation, we could do 1 plus 2 plus 3 plus 4 plus, well, we'd have to go all the way out until I equaled 200. Okay, so we could actually add all those numbers up, or we could use our formula. So recall, the sum from I equals 1 to n of I is n squared plus n over 2. So in this case, n equals 200. So we can really say 200 squared plus 200 over 2. And then we can use a calculator and come up with 20,100. So what we want to do is notice a couple things. We have to have I equals 1 down here. This becomes your n, and then use whatever formula we have for I right here. Once you get that formula, then you can substitute n in to solve for the summation. In example 2, we want to evaluate the summation for n equals 10, 100, 1,000, and 10,000. So first, let's go ahead and find our summation formula for I plus 2 over n squared. Now when we look at these, all of our n's are actually going to be constants. So this really can be rewritten now as the sum from I equals 1 to n, and we can factor out our constant. So we can really put 1 over n squared outside, and then we're left with I plus 2 on the inside. Now we can use the property where we have our addition of two functions in here.
So we would have 1 over n squared times our sum from I equals 1 to n of I, and then plus the sum from I equals 1 to n of our constant of 2. Now let's go ahead and use the formulas for each of the sums inside there. So we're going to get 1 over n squared times n squared plus n over 2, and then plus 2n. So I was just using my formula here for the I and for the 2. Now we can go ahead and simplify this by adding our fractions together inside. So to get a common denominator, we'll go ahead and change that 2 into 4 halves there so that we can add those. And so we'll get 1 over n squared times n squared plus 5n over 2. And now we'll go ahead and multiply across. So we have n squared plus 5n over 2n squared. And we can actually cancel an n out of this. So we're going to be left with n plus 5 divided by 2n. Okay, so that is our summation formula, turns into n plus 5 over 2n. Now what we want to do is we want to evaluate that for 10, 100, 1,000, and 10,000. So if n equals 10, then the sum would be 10 plus 5 over 2 times 10, which is 15 over 20, which is 0.75. If n equals 100, then our sum is 100 plus 5 over 2 times 100. And so we get 105 divided by 200, and that is 0.525. If n is equal to 1,000, then we have 1,000 plus 5 over 2 times 1,000, or 1,005 over 2,000, and that's going to be 0.5025. And the last one, if n equals 10,000, we get 10,000 plus 5 over 2 times 10,000, and that equals 0.50025. Now what we're trying to show here is that as n increases, what is happening to that summation? So 0.75, 0.525, 0.5025, and 0.50025. Well, the idea then is as n gets closer to infinity, your sum is actually getting closer to 0.5. We can see that numerically there. So in our next example,
We're asked to find a formula for the sum of n terms, and then use the formula to find the limit as n goes to infinity. All right, let's go ahead and try b together, since this one's quite a bit more difficult than this one. We do want to follow the same steps that we've been following, and whenever you're confronted with something that looks like this, we want to try to get rid of our squares and see if we can't write this as a polynomial first. Okay, so let's see if we can write this as a polynomial. So we're just going to be dealing with this part for now. So let's go ahead and square that, and that's going to be 1 squared plus 2 times 1 times 3i over n plus 3i over n squared, and then all of that is times 2 over n. Okay, so that was just squaring a binomial right there. Let's go ahead and simplify this a little bit. So this is going to be 1 plus, let's see, 2 times 1 times 3 is going to give me 6i over n. And then here, if we square this, that's going to give me 9i squared over n squared. And then this is all still multiplied by 2 over n. Now, it's still not quite in a polynomial form because we still have this multiplication. So let's go ahead and distribute this here. So we're going to get 2 over n plus 12I over n squared plus 18I squared over n cubed. Okay, so once we have a polynomial, let's go ahead and rewrite our sum and our limit formula here. So this is the sum. So I goes from 1 to n, and it's the limit as n goes to infinity. Okay, so we're going to just do this all at once. We've had a little bit of practice with finding this sum. So here you can see this is just a constant, and so our formula here is just going to be 2 over n times n. Okay, here we have a constant times I, so it's going to be that constant times n squared plus n over 2 from our summation formula. And here we have a constant times I squared. So that's going to give me 18 over n cubed times, well, I squared is 2n cubed plus 3n squared plus n over 6. Okay, and all of this we're finding the limit as n goes to infinity. Okay, so for each one of these terms now, you can use Bobo-Botten eats DC. So looking at this one, I can see my n's are going to cancel, so the limit is going to be 2. Okay, here, the exponents are the same, and so we're going to get 12 over 2, or 6. Okay, here we can also see the exponents are the same, so we're going to get 18 times 2 over 6. Well, 18 over 6 is 3 times 2 is also 6, and so this limit is going to equal 14. So that's how we can find the limit as n goes to infinity of our different summation notation formulas.